Welcome back to online lesson number 2. So I am going to continue on where I left off last class, and I will hopefully make this lesson a bit shorter than last in hopes to give you guys some time to work on your circulatory system assignment, which means I am going to plow through the rest of these notes and hopefully get it done in hopefully 20 minutes. So here we go. Cardiac output. So cardiac output is referring to the amount of blood that is being pumped from the heart each minute. So not everybody's cardiac output is going to be the same. So it is all dependent on two factors to how much blood is being pumped out by your heart each minute. So one of those things that is important to note is stroke volume. Stroke volume is talking about the quantity of blood being pumped by the heart with each beat. So basically this is saying how much blood can your heart pump out at one or during one contraction. So not everybody's stroke volume is going to be the same. So for example, if you have a bigger body, that typically means that you're going to have a slightly bigger heart, which means you're going to have a higher stroke volume because your heart is bigger in comparison to someone smaller. Now, looking at this in terms of a 5-year-old versus an 18-year-old, a 5-year-old's heart is going to be obviously a lower stroke volume than an 18-year-old's heart because their heart is going to be bigger than the 5-year-old. So greater contraction equals greater stroke volume. So this might also relate to if you are more physically fit versus not being physically fit. If you are more physically fit, then this allows your muscles of your heart to expand and contract a lot easier, thereby being able to create a stronger contraction versus someone who is not as fit. Now, the next important factor that plays a role in cardiac output is heart rate. So heart rate is the number of times the heart beats per minute. So sometimes we call this BPM or beats per minute. So BPM is just a shortened version of this, which I kind of alluded to in the last lesson. So BPM and normal BPM is between 60 and 100 beats per minute. Again, if it's lower than that, that would be considered bradycardia. And if it's higher than that, then that is referring to tachycardia, both being bad if over an extended period of time. So the calculation we use to measure cardiac output is taking our stroke volume and multiplying it by our heart rate, which is a very simple calculation. So what this means is on your exams, you are going to need a calculator. Doesn't have to be a very complex calculator. You could just use a calculator from the dollar store for this calculation, or you can do it in your head depending on how good you are at math. I prefer using calculators simply because what if the numbers changed? I always second guess myself on tests, so I just make sure I have a calculator. So here's our first question, and I'm only going to do one because it is a very simplistic calculation. So it says here, Lee has a stroke volume of 100 milliliters per beat. Okay, so stroke volume is a quantity of blood, which means that we're looking at milliliters. Quantity is talking about a number. Okay, so I'm going to go back up to stroke volume. I'm going to refer quantity to a number. Okay, so you have to have a physical number, and that's 100, right? So 100 milliliters is representing the quantity of blood, and then it says during each beat of the heart, which is why we have slash beat. Okay, so Lee has a stroke volume of 100 milliliters per beat and has a heart rate of 50 beats per minute. So every minute, his heart beats 50 times. Okay, so if I want to calculate his cardiac output, then what I need to do, and bear with me because it's easier to do calculations if I'm writing them out versus trying to type them out. So Lee, cardiac output equals, we are going to take his stroke volume, which is 100 milliliters per beat, and we are going to times it by his heart rate of 50 beats per minute. Now, if you are good at doing calculations and you plug this into your calculator, again, I don't want to second guess, so I'm just going to pop up my calculator. 50 times 100, oh, I probably should hit equals 5,000. Okay, so I have 5,000. Now 5,000 what? Okay, let's look at our units. So you can see here that we have where my cursor is, I have milliliters, and then on the bottom I have beat. So beat is on the bottom, it's my denominator. Now in my heart rate, I have 50 beats. A beat is on the top, and then minutes is on the bottom. So it would be easier if I did milliliters and then beat on the bottom instead of slash, but it's hard to do that with no pen. So what you actually can do here, I want to get my pen back here. I am going to cross off my beat here because that is technically a denominator. And then I have on the numerator or the top, I have beat as well. So that basically cancels each other out. Because if you have something on the top, something on the bottom that's the same, they cancel out. So then what I have left on the top is milliliters. And then what I have on the bottom is minutes. See, this would be bad if I had to actually write it out with my mouse pad here. So this means that I have 5,000, or Lee's cardiac output is 5,000 milliliters per minute. So every minute his heart can pump, if I want to convert that, is 5 liters of blood per minute. That's pretty darn good. Let's look at our next individual. We have Tom. Tom's cardiac output. He has a stroke volume of 50 milliliters per beat. And it says that he has a heart rate of 100 beats per minute. What does that actually equal? Well, if you take a look at Lee's is 100 times 50. Tom's is 50 times 100, and whenever you multiply the same numbers, it should come up with the same answer. So I have 5,000 milliliters per minute, or again, 5 liters per minute. So now this begs the question, what's the difference? Both Tom and Lee's cardiac output is the exact same. So how are they different? Is there one cardiac output that is better than the other? So Lee is pumping 100 milliliters with every beat, whereas Tom is only pumping out 50. Your body still needs oxygen, and this is always back to cellular respiration. So that being said, Tom has to, since his stroke volume is so low, he has to increase his heart rate in order to get the same amount of blood pumping through his body every minute. Whereas Lee, he's pumping out more blood every beat, so his heart doesn't have to work as hard. Okay, so I would hypothesize between these two individuals that Tom is, if all scenarios are the same and maybe they're at rest, then Tom would be more unhealthy than Lee. I would say that maybe Lee is more active in his lifestyle, whereas Tom is more sedentary. I can't even say that word. More, let's just say lazy at this point. Okay, so I would say Tom is probably less active as his heart cannot pump as much blood in each beat. So he needs to have his heart pump more each minute to move the same amount of blood as Lee. So his heart is working harder, which could eventually lead to a lot of circulatory system disorders. It could lead to a heart attack, for example. Okay, so that took me 10 minutes. Let's try to get a little quicker here, Bodner. So, blood pressure. So I am sure you've all been to the doctor and you've had your blood pressure taken. So the device that is actually measuring your blood pressure is referred to as a sphygmomanometer. Sphygmomanometer. So when you're measuring blood pressure is actually referring to the force. So the definition of blood pressure is talking about this first sentence. Okay, so the force of blood against the walls of the artery, and I did talk about this in our last lesson, so I'll try and go through this one fast. So the walls of the arteries, the more blood there is in the arteries, that causes more pressure on the artery walls. So this can be measured with a sphygmomanometer. Okay, so typically what they do is they put the cuff on, well, what they do nowadays is they put the cuff on your arm, they press a button, and then they walk away. And then they come back and read the numbers. But that's not how this was done even a few years ago. Well, it's probably been maybe 10, 20, 30 years maybe. So this device is one where the doctors would actually be listening for changes within your artery. So what they're going to do is they're actually going to inflate the cuff. So this works the same way as the electrical device that they press a button and walk away. Okay. You cut off the inflation of the cuff does is it cuts off blood flow to the brachial artery. The brachial artery is simply the artery that is found in your arm. The stethoscope is placed below the cuff. Air is slowly released until a low-pitched sound can be heard. So the low-pitched sound is when your heart is allowing the blood to start moving back into that artery. Okay, this they will then read as the systolic pressure. So you need to know that when they do this and they're measuring with this old style way, I guess you could say, is they listen for low-pitched sound being heard. Well, first they have to cut off blood flow and then they slowly allow blood to start coming through. The measurement is read on the sphygmomanometer. Okay, when they first hear the sound, then they read that number as systolic. As they slowly continue to deflate the cuff more, the sound will eventually disappear. And when that sound completely disappears, then that is read as the diastolic pressure. Anytime we are measuring blood pressure, it is always measured in millimeters of mercury because that was the old style of the measurement within the sphygmomanometer, and it was actually mercury that was in this device. Kind of looks like a thermometer. So it is always systolic over diastolic. So if you ever go to a doctor, actually ask them when they actually inflate the cuff, ask them what your blood pressure is. Okay. Typically, we look at normal blood pressure being around, and I'm going to highlight this for you. I want you guys to know this number. That was a really bad highlight. I'm sorry, guys, but I want this adult one, and it's under 120 and under 80 for diastolic. So when they use or are recording the numbers down, they'll say like 120 over 80. The 120 is talking about your systolic pressure, and then the 80 is talking about your diastolic pressure. So if you remember back to yesterday's lesson, systolic pressure is when your heart is contracting and the blood is ejecting from the heart. If it's ejecting from the heart, that means not all of the blood, but the blood is now in an artery. So that means there's more blood in the artery, which should mean that it is a higher pressure because there is more blood putting pressure on your artery walls. And then when you have systolic pressure is when your heart is relaxing and filling with blood, which means there's less blood in the in the arteries, which then means there's less pressure on the artery walls, causing a lower pressure. So if you note all of the readings here, you'll notice your diastolic pressure is lower than your systolic pressure. Now, the other unit or other number I really want you to know, besides the 120 over 80, 120 over 80 is typical and normal. Personally, my blood pressure when I'm at rest is probably 107 over 76-ish. So I run a little bit lower than what normal is here, and everybody will be different. But if you have high blood pressure, this is known as hypertension. Hypertension is characterized by any systolic pressure that is 140 and higher, okay? And diastolic pressure will be anything 90 and higher. So 140 over 90 and higher is referred to as hypertension. Hyper being high. Okay, so hypertension is referring to high blood pressure. Now, they're not going to use one unit of measure to determine whether or not you have high blood pressure. I've gone to the doctor before and they've measured my blood pressure, and sometimes it's on a slightly high end of the scale, like, I don't know, 136 over 87. Well, that's borderline, okay? You're getting a little bit higher. I know my blood pressure is pretty good, and I tell the doctor that's not normal for me. So typically what they'll do is they'll walk away and come back 5-10 minutes later and they'll do your blood pressure again. You can never rely on one diagnostic tool or one diagnostic test to diagnose someone with something. So typically, my blood pressure will go down after that. External factors can play a role in your blood pressure. So what if I bike to the doctor's office? Then my blood pressure will be slightly higher because my heart rate is higher and I have been exercising. If I drank a crap ton of caffeine before I went, that's going to cause my blood pressure to skyrocket as well. So blood pressure is dependent on other factors, which I kind of just talked about. So this is cardiac output. So increased cardiac output is going to increase your blood pressure because you have more blood in the arteries, causing more pressure on the artery walls. The next one is arteriolar resistance. So we talked about how we had constriction of the artery walls. Remember, there was arteriolar sphincters. Okay, so sphincters will constrict. What this means is if you have constriction of the arterioles, it means blood is basically being stopped going into the capillary bed. If it stops going into the capillary bed, that means that you're going to have a backlog. So this would be like a traffic jam. So now all of this blood is traffic jammed back up into an artery because it can't go anywhere. So what that means is you will have a slightly higher blood pressure at that point because the blood has to stay in the artery. Okay, it's got nowhere else to go until those muscles, those sphincter muscles will relax, allowing the blood to move through. Now, remember, constriction is going to happen only when the cells of the body or the cells of that area of the body have enough oxygen and glucose to carry out cellular respiration. So this is dependent on what your body is doing, how much oxygen it needs, how much CO2 it needs to get rid of, etc. So hypertension. We just talked about this. I want you to write beside hypertension, this is BP, blood pressure, higher than 140 over 90. Okay, and remember, we need to do multiple tests to determine whether or not it is hypertension. Okay. So regulation of blood pressure, just like heart rate and breathing rate. Sorry, I didn't stick to the 20 minutes, but I will keep going. Heart rate and blood pressure are regulated by the body. Okay. Blood pressure also has to be regulated by the body. So blood pressure receptors, okay, we had chemoreceptors in the case of the respiratory system, but blood pressure receptors are located in the aorta, okay, at the top of the heart, and the carotid arteries. Okay, the carotid arteries are located in your neck, so you might want to jot that down. Okay, and they are going to the brain. Okay, you have one on the left side and one on the right side. So if pressure becomes too high, they send a signal to the medulla, and the medulla is found within the brain. Okay, so basically what it's saying is the aorta and the carotid arteries will send a message to the brain to tell the brain that it needs to do something to decrease the blood pressure. So what's going to happen is the medulla is then going to decrease sympathetic nerve impulses and increase parasympathetic. So we talked about that last class. I'm sorry, my highlighting's so bad. But sympathetic is when your heart rate is higher, and typically when you have a heart rate higher, remember sympathetic response is when you're in that fight or flight response. So when you're in a fight or flight response, your heart rate and your breathing rate are higher, which means your blood pressure is also going to be higher because there's going to be more blood in the arteries for a longer period of time. So if you decrease those sympathetic nerve responses, that means that you're trying to bring your heart rate down and your breathing rate down, which will then also decrease your blood pressure. Now you also want to increase your parasympathetic nerve responses because that is the response that is bringing your body back to normal. And you're going to talk about those two in more detail in Bio 30, okay? But the vagus nerve here is the parasympathetic nerve that is sending the message to the heart, okay, to the blood vessels and to the lungs, okay. Vagus nerve is very important because it is bringing our body back to normal. Sympathetic nerves, okay, are located basically in the middle of the spine, whereas the parasympathetic nerve is located at the top of the spine. It takes longer to bring our body back to normal because it's further away from the heart, okay? If you put your hand on the back of your neck, that's really where your vagus nerve is, and that's far from your heart in comparison to if you take your hand, if you're flexible enough to put it between your shoulder blades. Well, between your shoulder blades is where your sympathetic nerves are actually coming from. So that's a lot closer to the heart, being that it will send that response a lot quicker. So circulatory system and exercises. So sympathetic nerves stimulate the adrenal glands, which are going to release epinephrine. So epinephrine is a very important hormone. This hormone is regulating a lot of things, and you'll talk about this more in detail in Bio 30. But what you really need to know of for Bio 20 is simply that when epinephrine is released, it's increasing oxygen delivery. How it does so is by releasing the red blood cells. Okay, if you release more red blood cells, this means that there's going to be more oxygen being able to be carried through the body. So when you're in that fight or flight response, your spleen is getting a signal to release red blood cells so that you can deliver more oxygen to the muscles of your body so that you can either run or flee. So the question I have at the bottom is asking you, why are heart rate and breathing rate related? Well, breathing brings in oxygen and carbon dioxide to the blood, but it doesn't pump, but the lungs do not pump. Therefore, we need the heart to pump the blood for the lungs to the body, and technically away from the body. Okay. So, and guys, I'm really sorry I'm not there. I can only do what I can do, and hopefully I'll be there tomorrow. Okay. Thermoregulation. Thermoregulation is talking about, well, therm being heat, regulating heat. So this is the maintenance of body temperature within a range that enables cells to function efficiently. Our optimal body temperature is maintained at roughly 37 degrees Celsius. And again, this is dependent on the person. Everybody's body temperature will be different. I have a sick kid now, and I know his body temperature. But his body temperature typically ranges from 36.5 to 37.1. That's his range. Anything higher than that, to me, that's my signal to say something's wrong. He's fighting something, he's sick, and whatnot. But everybody's is different. So roughly around 37 degrees Celsius is normal body temperature. So what can cause change to body temperature? Well, working out, exposure to sun, okay, and then the big one is sickness, okay. A fever is an important bodily process that happens, and we'll talk about that more in detail in our next chapter. So how do we regulate the temperature? I didn't talk about this anywhere else but in this picture. So if body temperature is too high, the brain is going to get a signal. Now, more specifically in the brain, it's talking about the hypothalamus. So the hypothalamus is a very important structure within our body, which again, you'll learn more in Bio 30. What the hypothalamus is then going to do is it's going to send a signal to the blood vessels near the skin, telling them to dilate, meaning get bigger. This means that we're going to have increased blood flow towards the skin. If blood is closer to the skin, that means that it's able to lose a lot of heat. So basically, we're trying to give our heat away to the environment. The other one that we like to do is sweat. Okay, so sweat glands, so we start sweating. As we start sweating, if these blood vessels are near to the skin and you have more blood near the skin, well, you have wet surface on your skin, and if there's any sort of wind or external airflow, then that's going to cool you up right quick. Okay, so these two things, I'll put dilate skin blood vessels. What this is going to do is it's going to decrease our body temperature. Okay, so then we're cooling. Once our body temperature has lowered, then basically we're turning off this pathway, and the pathway will no longer be active. So your hypothalamus will be like, okay, I'm a-okay. Now, if my temperature is too low, hypothalamus also sends a message to the body saying, oh, wake up, we got to do something. So the first thing that can happen, well, these two things happen at the same time, but skeletal muscles will start to contract. So this is shivering. When you're shivering, muscles are contracting. When muscles contract, they are trying to create heat or conserve heat. Well, they're not conserving heat, sorry. Body hair is going to help you try to conserve heat. Doesn't do as much nearly as the shivering does, but shivering tries to create heat because your muscles are moving. That's why when you're cold, keep moving, okay? And then the other thing is skin blood vessels are going to constrict. This is moving blood away from the skin, less likely for the heat that is in your body to be lost to the surroundings. So you want to try to conserve as much heat as possible. This hopefully increases your body temperature, and then your hypothalamus will basically be turned off. You should have done this on Monday. Okay. These are fair game for your test, so hopefully you've got it done. Capillary fluid exchange. So capillary fluid exchange, this is talking about the capillary beds within the body. So we know that our capillaries do this. So they also aid in fluid exchange between the blood and the extracellular fluid. This is referred to as the ECF from here on out. This is the fluid outside the capillary and outside the cells. So the ECF is very, very important because things that come out of the capillary bed and are trying to get into the cells, they first come out of the capillary bed and go into the ECF and then into the cells. So it's a step-by-step process. So we're going to focus on the exchange of water between the blood and the ECF. So there's actually two forces that play a role in the movement of movement of water between the ECF and the blood. So the first thing is fluid pressure. So fluid pressure is based on the arteriolar end of the capillary bed, which has a higher pressure. Okay, so I have this lovely diagram at the bottom here. I suggest right now that you pause the video and you kind of do a rough sketch. You don't have to have all of these here, but what I want you to do is sketch out kind of what you see and then label this. This is your arteriolar end, and this is your venual end. And then the middle here is talking about your capillaries. So when we're talking about fluid pressure, we're talking about the arteriolar end down here. And this is, or this side is high pressure. Okay, what happens is you have a very high pressure here on the arteriolar end. When the blood starts dividing between all of these little blood vessels, what happens is the pressure starts dropping. So I'm going to put down here lower pressure right in the middle here. Okay, so pressure's dropped. Okay, it's kind of like speed. When you're driving on a highway and then the highway branches, imagine into like 5 or 6 different paths. Are you going to be going to the same speed? No, you're going to have to slow down to make a decision to take one of the 6 roads. Kind of the same thing here. So the pressure will drop. So this means we have a high, so I'm going to go back up here. So on the arteriolar end of the capillary, we have high pressure, and the ECF has a lower pressure. So if you think back to our respiratory system, everything is going from high pressure to low pressure. So what water is going to want to do is it's going to want to move into the ECF. Along with water, we have ions moving with it. This process is known as filtration. Large molecules like proteins, red blood cells, and white blood cells are going to remain in the capillary. So I'm going to put on the bottom here, on the arteriolar end, we have filtration. And what this means is water moves out of arteriole to, and I'm going to try and make this stick to this side. Okay. I can make it bigger. I should have started over here. So water moves out of arteriole to ECF because ECF is lower pressure than arterial. Minerals will move with. Big things stuck in capillary. Okay. Now, on the opposite end, there we go. This is the venule end. This process is known as absorption. So absorption, we can't lose water to the ECF. It has to come back into the blood vessels, because if we lose water from the blood, then what happens is blood pressure is going to tank. Okay, because you have less water in the blood, and you do have water in your blood. You have water in everything. Okay, so what this means is the big things left in the vessels will draw water back into the capillary. I'm going to back into the venule end of the capillary. This will maintain our blood pressure. So this is known as osmotic pressure, and whereas your arteriolar end is fluid pressure. So these large molecules on the venous end or venule end will allow the water to be sucked back in, kind of like a sponge, and we are absorbing the water back in. Now, processes that can happen, or issues that can happen. Hemorrhaging. Hemorrhaging is referred to as excessive bleeding. This is a severe decrease in blood volume. Okay, this means that you will have a very low blood pressure. That is bad, because if you have low blood pressure, that means blood's not going to get anywhere in your body. So both proteins and fluids are lost during a hemorrhage, but the concentration of water to protein and fluids is the same. So this means that water or fluid pressure is not going to move, also put not, move out of the capillary bed. So what's going to happen is it's going to move into the capillary bed, restoring blood volume, or trying to. So when you are bleeding, or when you have excessive bleeding, what your body's going to try to do to fix it is the ECF, which is located out here. You see where my pen is up here? This is the ECF. Since this would be a higher pressure in comparison to your artery, because you're losing blood, less blood in the artery, less pressure, your ECF is going to give its water to the blood vessels in order to try to restore blood volume. Now, this might not necessarily work. It all depends on where the hemorrhage is happening and if they can fix it. Starvation is the next thing. Starvation is when the body is starting to use proteins as a source of energy. Proteins are found everywhere in your body. This might even mean the proteins found in your blood. And this is the energies are our last source of energy. This means you are going to decrease osmotic pressure. And what this means is, if I go back to this diagram over here, okay, the big things are no longer in here, which is what drew the water back in. If you don't have big things in here, the water stays here in the ECF. This then means that your tissues, which is where your ECF is, are going to start swelling. So you'll be very puffy, for example, and this is known as edema. Okay, because water is building in this body. Last thing is the lymphatic system. So normally small amounts of proteins do leak into tissue spaces. Our body kind of has a backup plan. So what it's going to do is we need to get rid of the extra proteins that have leaked out. And this is what our lymphatic system does. So our lymphatic system, so that's this paragraph here, The lymphatic system drains excess proteins into your lymph vessels. I talked about the lymph vessels once before in the small intestine, and this is where your fats are absorbed into, and then it goes back into your blood vessels. Okay, so what the lymph vessels are simply going to do is they're going to suck those proteins out almost as if you're vacuuming them out of the ECF. So here you can see the yellow, that's the ECF, and this is and these little cells are obviously the cells of the body. These vessels are filled with lymph, which is a substance very similar to blood, but it's not blood. These vessels also have valves and use muscle contractions to move the proteins as well as the lymph back into the circulatory system in the veins. So basically what you need to know from this is the lymph vessels will clean up any extra proteins that have leaked out and bring them back to the circulatory system. Lymph nodes, on the other hand, are masses of tissues that store lymphocytes, which are white blood cells. I'm going to talk about this in the next chapter. This is going to remove bacteria, foreign particles, and damaged cells from the lymph. So lymph nodes, you'll notice that sometimes when you're sick, the doctor feels, and you can feel this right now, right under the jaw, the back of your jaw. You have lymph nodes located there. And when you're sick, sometimes they swell up, and they swell up because they have lots of white blood cells. And when you're fighting infection, you have more white blood cells, which means the lymph nodes are going to get bigger because there's more white blood cells. The other parts of the lymphatic system are the spleen, and this is where the lymph is actually filtered and where you have your storage of your red blood cells. Bone marrow, which produces stem cells, which gives rise to specialized blood cells being both red and white, and I'll talk about this more in the next chapter. And then the thymus gland. The thymus gland is where T lymphocytes, again, I'll talk about this in the next chapter, are going to be made and mature. For now, I would really know number 2 and number 1 for this chapter. And then this is just a diagram showing you where your lymph nodes are and where you have your lymph, and it's throughout your body just like all of your other blood vessels. That is the end of the video. I am sorry that it took me longer, but it is what it is. You now have time to work on your circulatory system assignment.